Okay, I want to talk a little bit about electrolytes. So broadly speaking, what is an electrolyte? Well, essentially it's an ion in solution. So let's remind ourselves, what is an ion? Well, an ion is any atom or compound that has a charge. So just as a very simple example, let's say I've got potassium with a +1 charge. If I throw this into a solution, if I throw that into a bucket of water, boom, it's an electrolyte. So how did they get their name, electrolyte? Well, a long time ago, scientists discovered that when you put things in solutions that make ions, the solution was actually able to conduct electricity. And when you put certain ions into the solution, the electricity was conducted more strongly. And they tested things out like acids, bases, and salts. So acids, bases, and salts are the three main divisions of electrolytes. And while these aren't electrolytes in and of themselves, they are divided into things that ultimately make electrolytes. So let me explain. So among acids, you generally divide them into strong acids and weak acids. And we generally say strong acids are strong electrolytes, while weak acids are weak electrolytes. So what's an example of a strong acid? Well, HCl, hydrochloric acid. So why do we say this is a strong acid? Well, it's because when you have HCl, it dissociates into its respective ions almost completely. So let's say we started out with 5 molar concentration of HCl. We're going to end up, after you put this into a solution, with 5 molar concentration of H plus and 5 molar concentration of Cl minus, with almost 0 molar concentration of HCl. So it almost completely dissociates into its respective ions. Therefore, it contributes a lot of electrolytes to the solution. So therefore, we call this a strong electrolyte. So weak acids, on the other hand, they don't dissociate into their respective ions to nearly the same extent. So for example, if we started out with 5 molar hydrofluoric acid in a solution, we may end up at the end, after it's completely dissociated, with 0.05 molar H plus and 0.05 molar F minus, remaining, with 4.95 molar HF. So it really doesn't dissociate to nearly the same extent that the strong acids do. Therefore, it contributes less ions to the solution. So we call it a weak electrolyte. The same exact concept holds true for strong bases and weak bases. The only difference is the weak bases generally contribute hydroxide ion to the solution, while strong acids and weak acids generally contribute hydrogen ion to the solution, or H plus. So the final division of electrolytes are salts. And you generally will see salts divided into soluble salts and insoluble or partially soluble salts. So soluble salts, these are strong electrolytes because they completely break up into their ions. So for example, NaCl, that's a soluble salt because it completely breaks up into Na plus and Cl minus, thus contributing a ton of ions to the solution, which are electrolytes. An insoluble or partially soluble salt, on the other hand, like calcium sulfate, is not going to break up much. It's going to stay as a solid in the solution. It's like you drop a solid brick of calcium sulfate into a solution and it's just going to stay there. It's not really going to dissolve. So you're not going to contribute much ions at all to the solution, and thus you're not going to have many electrolytes in the solution. So you can think about, a long time ago when they were first discovering this, they probably thought it was really interesting that when you hook up 2 electrodes to a solution and then connect them to a light bulb, and then you pour in HCl, the light bulb actually shone brighter than when you poured in hydrofluoric acid. So the stronger the electrolyte, the more electricity conduction. So I hope that makes sense. Okay, so I know this looks like a lot, but it's really not that bad. So let's walk through this slowly. So we say a 2-liter solution contains 93.5 grams of aluminum sulfate and 23.7 grams of sodium sulfate. What are the molar concentrations of aluminum, sodium, and sulfate ions? Well, this is the first time we've seen molarity in this video series, so let's talk about that briefly. So molar concentrations refers to molarity, which is defined as moles of whatever you're looking at over liters of solution. So if we want the molar concentrations of aluminum, sodium, and sulfate ions, we need these 3 things. We need moles of aluminum over 2 liters of solution, moles of sodium over 2 liters of solution, and moles of sulfate over 2 liters of solution. So notice how I haven't filled in any of the mole amounts. That's because we don't have them yet. But we do have the total solution volume, right? Total liters of solution. That's why I've already filled in the denominator. So now, once we know what molarity means, this is essentially a stoichiometry problem, just like from one of the previous lectures. So we really just need moles of aluminum, moles of sodium, and moles of sulfate. And we know that with any stoichiometry problem, we need a balanced chemical equation, right? So the first thing you do is you write that out. So what's going to happen when I put both of these into a solution? Well, they're going to break up into their respective ions, right? And we know aluminum sulfate is made up of 2 aluminum atoms and 3 sulfate atoms. I'm sorry, 3 sulfate compounds. And then sodium sulfate is made of 2 sodium ions and 1 sulfate compound. So now we have balanced chemical equations. And let's remind ourselves, how do we get from initially grams of reactant to moles of product? Well, let's go atom by atom. So let's start with aluminum. So for aluminum, the only place that aluminum was produced was in this first reaction. So we'll take grams of what we were initially given, grams of this reactant, change that to moles so that we can cross our mole bridge and go to moles of aluminum, and that'll be what we want. So we'll take our initial amount of aluminum sulfate, change it to moles of aluminum sulfate, cancel these units out, and then we'll change moles of aluminum sulfate to moles of aluminum, right? Cancel these units out, and we end up with our desired units of moles of aluminum. And when you multiply all the numerators out and multiply all the denominators out and divide those two numbers at the end, you should get 0.55 moles of aluminum. And then we know we have to divide that by 2 liters to get concentration in molarity. So we find our concentration, our molar concentration of aluminum is 0.27 molar aluminum. So we do the same exact thing for sodium now. So the only place sodium was produced was in this second reaction. So sodium sulfate goes to 2 sodium plus sulfate. So we do the same thing, start with grams of sodium sulfate, and then we get 2 moles of sodium sulfate. By canceling these units out, we know from the periodic table that there are 142 grams of sodium sulfate per 1 mole. We know how to calculate molecular weights now. And then we'll change moles of sodium sulfate by canceling these units out into moles of sodium. And we know that from the balanced chemical equation, for every 2 moles of sodium, there are 1 mole of sodium sulfate. So when you do all the math here, you get 0.33 moles of sodium, divide that by 2 liters, and you get your molar concentration of 0.167. So the only thing that's slightly different about sulfate is that notice it was made from both reactions. So we're actually going to have to figure out the moles that was made from the first reaction and add it to the moles that were made from the second reaction. So for the first reaction, let's start with aluminum sulfate. We do the same exact thing we did before, just for sulfate. So I'm not going to run through this again. You guys know how to do this by now. We start out with grams of aluminum sulfate, and we end up with moles of sulfate. And once you do all this math, you get 0.82 moles of sulfate. And then when you do the same thing for the second reaction, you end up with 0.167 moles of sulfate. You add those together, and you get 0.987 moles of sulfate. Simply divide that by 2 liters as we did before, and you end up with 0.4935 molar sulfate. So it looks like a scary problem, but it's really not that bad. It's just stoichiometry kind of dressed up in a bow of molar concentrations. So please let me know if there are any questions about that. Okay, this problem asks us to calculate the molarity of chloride ions in a 375 milliliter solution containing 38.2 grams of NaCl and 0.268 moles of NaCl. So don't worry about any of this right now. I just want to remind us that molarity of chloride ions is equal to total moles of chloride ions over total liters of solution. That is our ultimate goal. Total moles of chloride ions over total liters of solution. So we were already given total liters of solution, right? 375 milliliters, which we know is just 0.375 liters. So ultimately what we really need to do for this problem is find the total moles of chloride ions. So we were given grams of NaCl and moles of HCl. And we know that these both end up making chloride ions, but how do they do that? So the first thing you should do is write out these reactions here and show how sodium chloride, or NaCl, dissociates into sodium and chloride ions, and then HCl dissociates into H plus and chloride ion. So you should also remember that sodium chloride is a soluble salt and HCl is a strong base, a strong acid. So that means that this salt will completely dissociate into its ions, and this acid will completely dissociate into its ions. So that means that whatever mole amount that we start with of HCl will end up with the same molar amount of H plus and Cl minus, and whatever molar amount we start out with of NaCl will end up with the same molar amount of Na plus and Cl minus, because they completely dissociate. So all of this will turn into this, all of this will turn into this. Make sure you understand that. So we started with grams of NaCl, and we've done problems like this before. We know that if we want to get grams of a reactant to moles of a product, we can cross the mole bridge. So we go from grams of NaCl to moles of NaCl, and then finally to moles of Cl. So we start with grams of NaCl, we convert to moles of NaCl using its molecular weight. These units will cancel out. And then we change to moles of Cl, and we cancel out these units, and we know that for every 1 mole of chloride, there's 1 mole of NaCl. So when we do the math here, we get 0.654 moles of chloride ion from the sodium chloride. Now, 0.268 moles of HCl, this is even easier, right? We're already in moles of HCl, so all we have to do is cross the mole bridge. So 0.268 moles of HCl is simply going to be 0.268 moles of chloride ion. You can see it's because they have a 1-to-1 molar ratio. So all of these compounds and atoms have a 1-to-1 molar ratio. So if you have 1 mole of this, you have 1 mole of this. If you have 1 mole of this, you have 1 mole of this. Same applies for the second reaction. So really, when you multiply by 1 over 1, you're really not changing anything. If you could just look at this and know that, okay, the moles of NaCl are going to equal the moles of Cl, you don't even have to do this part. But ultimately, we're going to add together the total moles of chloride to get our numerator here, and we get 0.922 moles of chloride over 0.375 liters, and we end up with a final answer of 2.46 molar chloride concentration. Okay, moving on to some dilution problems. So these are two fairly straightforward dilution problems, and for dilution problems you use this formula here. So this is probably one of the simplest equations that you'll learn in Gen Chem. It says that the initial molarity times volume is equal to the final molarity times volume. And you can use this with any solution that you're concentrating or diluting. And you can think about how it makes sense. You know, when, for example, if this volume were to go up, the molarity would have to go down to keep this side equal. So like when you add more volume to a solution, you're diluting it, so the molarity goes down. So let's look at a couple examples. So how many milliliters of 7 molar HCl is required to make a 200 milliliter solution of 0.4 molar HCl? So you kind of have to dissect out of this, what is your initial variables and what are your final variables? And another thing that you can't get tripped up on is when you pick a unit for volume, it has to be the same for both V's. So for example, if I use milliliters here, I have to use milliliters here. So my initial solution, they're asking how many milliliters of this initial solution is required to make a final 200 milliliter solution of 0.4 molar HCl. So my initial solution, I know the concentration, right? I know the molarity, it's 7, but I don't know the volume. That's what they're asking for. They're asking how many milliliters. So I'll solve for this. And then I know the final concentration is 0.4 molar and the final volume is 200 milliliters. And notice I picked milliliters for this volume here. So when I solve for V, I'll get it in milliliters. So this is very basic math now. We just divide both sides by 7 and then 0.4 times 200 over 7. You get 11.43 milliliters. So that's how many milliliters of 7 molar HCl that we have to use to make 200 milliliters of a 0.4 molar solution. So next problem, what volume in milliliters of 17 molar HCl must be added to water to make 11 liters of 0.845 molar HCl. So again, what is our initial solution here and what are they asking for? Well, they say what volume in milliliters, so we'll pick milliliters for our volume units of 17 molar HCl. So this is our initial solution. We have 17 molar of an unknown volume and we want to make 0.845 molar of an 11 liter solution. Notice I'm using milliliters, so I had to change 11 liters into 11,000 milliliters. So then I simply divide both sides by 17, this will cancel out, and I get 0.845 times 11,000 divided by 17, and you should get 546.77 milliliters. Okay, these are the last two problems I'd like to do for this video. So what volume of a 0.45 molar solution can be prepared from 19 grams of potassium carbonate? So I'll draw your attention right here, and we'll note that the first thing we know is that 0.45 is the molarity, which equals moles of potassium carbonate. By the way, this is the molecular formula for potassium carbonate, and you should know that per 1 liter of solution, right? Or any amount of liters of solution. This is just the general definition of molarity, and they gave us the molarity 0.45. So we have the molarity, they want volume, so they want liters of solution, so we need moles somehow, right? How do we get moles of potassium carbonate? Well, we know we can go easily from grams of potassium carbonate to moles of potassium carbonate by simply doing this conversion here. So we do 19 grams over the molecular weight of potassium carbonate, and then these units cancel out, and then we're left with moles of potassium carbonate on top. And you end up with 0.14 moles. So that means 0.45 molarity equals 0.14 moles over some volume in liters of solution. So we simply solve for liters of solution. Using algebra, we multiply both sides by liters of solution and then cross out the 0.450, and you get liters of solution equals 0.31 liters or 310 milliliters. Okay, the second problem says if the concentration of sodium in an aqueous solution of sodium phosphate is 4.3 times 10 to the negative 1 molar, how many grams of sodium phosphate must have been dissolved in 600 milliliters to make the solution? So the first thing I did here was I wrote out my chemical equation. And you should know that sodium phosphate is Na3PO4 because sodium has a +1 charge while phosphate has a -3 charge. So we need 3 sodiums to bond with 1 phosphate to make it an overall negative compound. So this is going to dissociate into 3 sodium ions and 1 phosphate ion. So the first thing I'll note here is that they told us 4.3 times 10 to the negative 1 is the molarity. Well, what does this mean? This means that 0.43 moles of sodium are in this solution for every 1 liter of the solution, right? This is the concentration of sodium. So 0.43 molars of molar sodium per 1 liter of solution. But we didn't have a full liter of solution, right? They told us that we had 600 milliliters of solution. So in order to figure out how many moles of sodium I would have in 600 milliliters of solution, I'm going to set up a proportion here. So 0.43 moles of sodium for 1 liter of solution is how many moles of sodium per 0.6 liters of solution, which is 600 milliliters. So I simply cross multiply here. I'll multiply this times this, and I'll get 0.6 times 0.43 equals this times this. 1 times x is simply x. And then we do 0.43 times 0.6. So we know that in 0.6 liters of solution, we must have only had 0.258 moles of sodium. Well, what are we ultimately looking for here? This gets us closer, but what are they asking for? They're asking for grams of sodium phosphate, right? That we must have had to dissolve in that 600 milliliter solution to make this molarity of sodium. So we have moles of sodium, right, in our 600 milliliter solution. We just got that. We know we can change that into moles of sodium phosphate because we have the stoichiometric coefficient. We're simply crossing the mole bridge. And then once we have moles of sodium phosphate, it's fairly easy to change that to grams as long as we know its molecular weight. So I went ahead and did that right here. We know we had 0.258 moles of sodium, and then we crossed the mole bridge. We're going to cancel out moles of sodium down here, and then go to moles of sodium phosphate. There are 3 moles of sodium for every 1 mole of sodium phosphate. Then we'll cancel out the sodium phosphate moles down there by going to grams of sodium phosphate. We know from the periodic table 3 sodiums plus 1 potassium plus 4 oxygens makes 164 grams per mole of sodium phosphate. And then we simply do the math here, multiply the tops, multiply the bottoms, top divided by bottom, and we find out that we must have needed 14.1 grams of sodium phosphate in order to make an aqueous solution with a sodium concentration of 4.3 times 10 to the negative 1 molar and a volume of 600 milliliters. So that's the end of this video. I really hope this helped you guys out. Please contact me with any questions on my Facebook page, facebook.com/denovotutoring. Thanks a lot, guys.